Model development is where the features start turning into predictions, and those predictions become something you can test and improve. The focus here is choosing algorithms, iterating on them, and checking whether the model is ready for production. The earlier work on training data and features pays off at this stage because the model turns that preparation into measurable outputs. Those outputs let you judge whether the data work was effective and whether the system is moving in the right direction. The first decision is not about fine-tuning details, but about choosing the algorithm family that fits the task. That choice shapes everything that follows, so the chapter starts with practical guidance for narrowing the options. Model development includes a lot more than fitting a model once. Good practice means being able to debug failures, track experiments, keep versions straight, scale training when needed, and use automation carefully when it helps. Each training run should be treated as one step in a loop, not as a final answer. The real question is whether the new version beats the old one and whether it behaves well enough to survive real-world use, which is why evaluation methods like perturbation tests, invariance tests, calibration, and slide-based checks matter. The chapter builds on core ML knowledge rather than teaching the algorithms from scratch. If those model families feel unfamiliar, it helps to review them first because the techniques here depend on understanding how they behave and how they fail. Model development and training is where the practical decisions start to matter. How to compare candidate models, how to combine them, how to keep experiments organized, and how to train at large scale. Those choices determine whether a model is just promising on paper or actually usable in practice. A good workflow starts by evaluating several model choices against the problem, then combining strong models when an ensemble can improve results. After that, experiment tracking and versioning keep the work reproducible. Distributed training makes large models feasible, and AutoML can automate model selection when the search space is broad enough. Choosing a model is really a decision problem. You want the method that fits the task, the data, and the constraints best. The important part is not just picking a model that works, but learning how to compare options in a way that matches real-world needs. A task often has more than one reasonable model behind it. So the question becomes which option deserves your time. One person may start with a familiar baseline, another may suggest a stronger model, and a colleague may point to something that worked well before. Evaluation is how you sort those choices out. If resources were unlimited, you could test everything and simply keep the best result. In practice, training runs cost time and money, so model selection has to focus effort where it is most likely to pay off. People often frame model choice as classical methods versus neural networks, but that distinction can hide the bigger picture. Deep learning has driven much of the recent progress, yet it did not make earlier methods obsolete, and both families still matter depending on the job. Many production systems still rely on older methods because they are fast, reliable, and good enough for the problem. Recommenders, gradient-boosted trees, and other tree-based models still solve important tasks, especially when latency matters. The real world is rarely a pure choice between one model family and another. A clustering method can create features for a neural network, or a pre-trained language model can produce embeddings that a simpler classifier uses downstream. The first step is to identify the task type, because that narrows the model set to something sensible. For toxic tweet detection, text classification models like naive Bayes, logistic regression, RNNs, and transformers are natural candidates. A fraud system usually looks for unusual cases rather than ordinary ones, so the model search changes with that framing. Methods like k-nearest neighbors, isolation forest, clustering, and neural networks can all play a role, depending on the data and the operational setting. That mapping between tasks and typical approaches is one of the most useful things to learn early. It helps you avoid random model picking and move faster toward a reasonable first experiment. Different algorithms place different demands on the project. Some need lots of labeled data, some train slowly, some are slow at prediction time, and some are easier to explain than others. Accuracy, or F1 score, matters, but it is only one part of the decision. A lower accuracy logistic regression model may still win if it trains faster, needs less data, deploys more easily, and gives clearer explanations than a more complex neural network. A comparison can become outdated very fast because the field changes so quickly. What looked dominant a few years ago may be replaced by a different architecture once the community finds a better way to solve the same family of problems. The most reliable way to understand an algorithm is to work with it directly and test it on your own data. Staying current also means watching strong research venues and paying attention to work that consistently produces useful results. The next part collects a few practical habits that make model choice more disciplined. These are less about any single algorithm and more about how to avoid common mistakes when comparing options. The point of these tips is to help you choose a model with clearer judgment, not with more excitement. Each one pushes the decision toward the task, the data, and the deployment reality. A common mistake is assuming the newest model must be the best answer. That mindset can waste time, money, and effort if the flashy option is unnecessary for the actual job. People are often drawn to the newest model because it sounds superior or more modern. But enthusiasm is not evidence, and a model that looks exciting on paper may not be the right tool for a business problem. A model can earn that label by performing well on fixed academic datasets, which is a narrow test of usefulness. That same model may be too slow, too expensive, or simply worse on your data. The goal is to solve the problem, not to prove you can deploy the most advanced architecture available. When a cheaper and simpler model gets the job done, that is usually the better engineering choice. Simplicity gives you a clean starting point. It helps with deployment, debugging, and building a baseline that tells you whether more complexity is actually buying anything. A simple model lets you validate the full pipeline early, from training all the way to prediction. It also gives you a reference point, so later improvements are measured against something concrete instead of guesswork. A pre-trained model can be quick to start using even though the underlying architecture is quite complex. That can be a good choice, but it is still worth checking whether a simpler approach matches or beats it before you commit. Model evaluation is also vulnerable to people's preferences and habits. If one architecture gets more attention and more tuning time, it can look better for reasons that have little to do with the architecture itself. Suppose one engineer spends weeks tuning BERT and only a little time on gradient-boosted trees. The comparison may reflect effort and balance more than real model quality, so the result can be misleading. A different engineer may revisit the other model family with a fresh search and find a stronger configuration. That kind of reversal usually means the first comparison was incomplete, not that the earlier team was careless. The search process matters as much as the final score. If one side gets many more experiments, more feature work, or more tuning, the result is not a fair test of the architectures themselves. A fair comparison means giving both candidates a similar amount of search effort. Otherwise, the better result may simply belong to the model that was explored more thoroughly. A model does not live in a vacuum. It depends on the task, the training data, the test data, and the tuning process. Because of that, broad claims that one architecture is always better are usually too strong. A model should be judged not only by how it behaves today, but also by how it might evolve as the system grows. That matters when data volume changes or when one method can improve more easily than another. A tree-based model can be the better choice when data is scarce, while a neural network may improve a lot once more data arrives. Planning for that shift can change which model is worth investing in now. A learning curve plots performance against training set size, so it gives a quick sense of whether more data is likely to help. It will not predict the exact gain, but it can tell you whether the model still has room to improve. The important comparison in the figure is how the two curves change as the sample size increases. One curve may flatten early, while the other keeps improving, and that shape tells you a lot about whether extra data is worth collecting. The focus should be on the gap between the curves and whether either one is still climbing. A steep rise suggests room for more data, while an early plateau suggests that a different model or feature set may matter more. A model that can update continuously may start out behind a more traditional method, but that advantage can disappear once fresh data keeps arriving. In that kind of setup, deployment is not a one-time decision. The update strategy is part of the comparison. A fair evaluation includes how much headroom each model has and how hard it is to reach that headroom. A model that is slightly worse now may be the better investment if it can improve much more easily later. Model choice is often a trade-off between competing goals rather than a search for a single winner. The right answer depends on which cost, risk, or constraint matters most in the system. Once you know what matters most, the comparison becomes much clearer. The best model is the one that gives the right balance of quality, speed, cost, and usability for that specific application. Many classifiers face a tension between missing bad cases and incorrectly flagging good ones. Which mistake hurts more depends on the task, so fingerprint access and medical screening require different preferences. A more accurate model may need more hardware and still be harder to explain. Sometimes a slightly less accurate model is the better system because it is cheaper to run and easier for people to trust. Every model works only because it assumes something about the data or the problem structure. If those assumptions do not match reality, the model may look good in theory and fail in practice. That quote captures the basic idea well. Models are approximations, not reality itself. What matters is whether the approximation is useful enough for the task at hand, and that depends on its assumptions. The list that follows is not exhaustive, but it gives a useful way to think about model fit. Each assumption is a question you can ask before trusting a method on your data. The first assumption is very basic. Can the output actually be predicted from the input? If there is no real signal in the input, no model can manufacture one. Any predictor starts by assuming that the input contains enough information to estimate the target. If that relationship does not exist, model selection will not fix the underlying limitation. Some models rely on examples behaving like independent draws from the same distribution. That assumption simplifies learning, but can break when the data has time structure, drift, or repeated dependencies. For neural networks, that means each example is treated as coming from the same overall data generating process and not being tied to the others. When that is not true, the model may need extra care or a different formulation. Another common idea is that nearby inputs should lead to nearby outputs. Without that kind of regularity, Learning from examples becomes much harder because the model cannot generalize from one point to the next. Supervised learning depends on some continuity in the mapping from inputs to outputs. If a tiny change in the input can cause a wildly different label, most standard methods will struggle to learn a stable rule. Some models are mathematically well-defined, but computationally impractical. A useful method has to be not only conceptually sound, but also feasible to compute with the resources available. For a generative model, the latent representation needs to be obtainable from the input in a way the algorithm can actually handle. If that probability is too hard to compute, the method becomes difficult to use in practice. Some classifiers assume a particular shape for the decision boundary. That assumption matters because it directly limits the kinds of patterns the model can separate well. A linear model can only separate classes with a straight boundary in the feature space. If the true boundary is much more curved, the model may need richer features or a different algorithm. Naive Bayes is built on a strong, simplifying assumption about the features. Even when that assumption is not perfectly true, the model can still be useful, but it is important to know what it is assuming. The model treats each attribute as if it carries separate information once the class label is known. That makes the math simple, but it can miss interactions between features. Some statistical methods work best when the data follows a bell-shaped distribution. If the data is far from that shape, the method may still run, but its assumptions become questionable. That assumption is common in statistics, so it is worth checking before relying on the result. When the data does not look roughly normal, a transform or a different method may fit better. Ensembles combine several models, so the final prediction is usually steadier and more accurate than one model alone. The main idea is to let multiple learners share the work and reduce the chance that one bad decision dominates. A base learner is just one model inside the group. For classification, each model votes, and the ensemble follows the majority, so a few weak opinions can turn into a stronger decision. Competition settings favor every extra bit of accuracy, so it is common to see many strong models combined together. That pattern is a clue that ensembling is often worth the added complexity when performance matters a lot. In production, the trade-off changes. Multiple models mean more moving parts to serve and maintain, so ensembles are most attractive when a small lift in accuracy has a large business value. The figure reinforces that point. The strongest Squad 2.0 systems are all built from combinations of models. The important idea is not the benchmark itself, but the repeated pattern that ensembles keep showing up near the top. That ranking is a useful signal that combining models can push performance past what a single model usually reaches. The next step is to ask why the combination helps mathematically. A simple majority vote can beat each individual model if their mistakes are not happening on the same examples. With three independent classifiers, the ensemble wins whenever at least two are correct, and that is enough to raise accuracy. The table breaks the result into cases. All three correct and exactly two correct both count as wins for the ensemble, and those probabilities add up to 0.784 or 78.4%. The useful split is between the cases where the majority is right and the cases where it is not. Once fewer than two models are correct, the vote goes the wrong way, and the ensemble loses that example. This game depends on the models making different mistakes. If they are too similar, the same error repeats across the group. So diversity in model type is what makes the vote more valuable. Those are the three main ways to build an ensemble. They differ in how the models are trained and combined, and bagging is the place to start because it gives the cleanest intuition. Bagging is about training many versions of the same idea on different sample datasets. The goal is to make the final model less sensitive to noise in the training set. Bootstrap aggregating means sampling the data with replacement and then aggregating the predictions. That averaging effect mainly cuts variance, which is why bagging often helps unstable learners that tend to overfit. Each bootstrap is a slightly different dataset drawn with replacement from the original data. Training one model per bootstrap creates a set of learners that are similar in method but different enough to benefit from aggregation. The diagram should make the sampling step feel concrete. One original dataset feeds several bootstraps, and each bootstrap trains its own model. The key pattern is repeated training on resampled data, not a single shared split. That picture ties the resampling idea to the ensemble output. After several bootstrap models are trained, their predictions are merged into one result instead of trusting any one tree or classifier alone. For classification, the final class comes from the vote across models. If most of them say spam, the ensemble says spam, even if a minority disagrees. For regression, the outputs are numeric, so the natural combination is the mean. Averaging smooths out extreme predictions and gives a more stable estimate. Bagging pays off most when a model changes a lot from one training sample to another. Stable methods already behave consistently, so they have less room to improve and may even lose a little precision. Random forests are the classic bagging example. Each tree sees a bootstrap dataset and only a random subset of features, and that extra randomness makes the trees less correlated. Boosting builds models one after another instead of all at once. Each new learner tries to fix the mistakes made by the previous ones, so the ensemble gets stronger stage by stage. The training data stay the same, but the importance of each sample changes from round to round. Misclassified examples get more weight, so later learners spend more attention on the hard cases. Follow the arrows in the figure. Train one weak learner. Measure where it fails, then raise the weight of those failures before training the next learner. That feedback loop is the core mechanism behind boosting. The picture is useful because it shows the sequence rather than a one-shot vote. Boosting is not about independent models. It is about a chain of learners correcting earlier error patterns. The numbered list marks the steps in order, so the logic is easier to follow one stage at a time. Training begins with a simple learner on the unmodified data. That first model gives you a baseline and also reveals where the hardest examples are. The second marker keeps the sequence clear, since each pass depends on the result of the previous one. This is the correction step. Samples that the first model got wrong matter more now, so the next learner is pushed toward those difficult examples. The numbering continues because boosting is a repeated cycle, not a single retraining step. The second model sees the same data, but through a different lens. Hard examples count more. After that model is added, the ensemble already has more capacity than either learner alone. Another step marker keeps the repeated training process easy to track. After combining the first two models, the weighting is updated using the ensemble's mistakes, not just one learner's mistakes. That keeps the later models focused on what the current ensemble still gets wrong. The repeated numbering signals that the process continues in the same pattern for each round. Each new learner joins a growing weighted collection. The important idea is that the ensemble becomes stronger by adding models that specialize in the remaining errors. The list still just marks the next iteration in the boosting cycle. The process keeps going until the model is strong enough or another stopping rule is met. More rounds usually mean more opportunity to correct mistakes, up to the point where extra complexity stops helping. The final step marker leads into the way the learners are combined at the end. The final boosted model is a weighted sum of the learners. Better learners get more influence because their lower training error is evidence that they deserve more say in the final decision. Gradient boosting machines are one common boosting method. They usually use shallow decision trees and add them stage by stage while optimizing a chosen loss function, which makes the method very flexible. XGBoost became popular because it performed well in many competition settings, and light GBM is often preferred when speed matters on large data. Both are gradient boosting frameworks, but they make different engineering trade-offs. Stacking combines models in a different way. Instead of hand-designed voting, a second model learns how to blend the outputs of the first ones. That makes the combination itself a learning problem. The base learners make first-level predictions, and the meta-learner turns those predictions into the final answer. In simple cases, the combiner is just a vote or an average, but it can also be a separate model like logistic regression. Track the flow from left to right. Several base models produce outputs. Those outputs become features for the meta-learner, and the meta-learner produces the final prediction. That layered structure is what makes stacking different from a plain vote. The diagram closes the chapter on stacking by showing the two levels clearly. First-level models do the initial prediction work, and the top-level model learns how to trust them in combination. A good follow-up is the ensemble guide from ML Wave, since it gives practical advice from a team with strong competition experience. That kind of reference is helpful when the goals shift from understanding the idea to choosing the right ensemble method for a real problem. Experiment tracking and versioning are what make ML work reproducible instead of mysterious. The focus here is on recording what changed, what happened during training, and what you would need to rebuild the same run later. Training often involves many similar runs, and a tiny change in a hyperparameter can lead to a very different result. Keeping the important artifacts and settings lets you compare runs, understand why one model behaves better than another, and recover the details when you need to revisit the experiment. Experiment tracking focuses on what happened during training, while versioning focuses on preserving the exact ingredients of the run. In practice, the two overlap a lot, which is why tools in both categories now tend to support both capabilities. Tracking starts with watching the training process closely enough to catch trouble early. The goal is to see whether the model is learning, whether it is wasting time, and whether the numbers tell a sensible story. Training can go wrong in many ways. Loss may stall, the model may overfit, gradients may behave badly, or memory may run out. If you record the right signals during training, you can spot those failures sooner and judge whether the model is actually improving. People used to track only a couple of numbers, but the set of useful signals has grown a lot. The point is not to collect data for its own sake. It is to leave clues that help explain why a run succeeded or failed. Start with the core metrics, and then add other signals only when they help you understand training more clearly. Loss curves show whether optimization is moving in the right direction and whether the training and evaluation behavior are diverging. A widening gap between them often gives the first hint of overfitting. That curve is one of the fastest ways to see whether training is healthy or drifting off course. Accuracy, F1, perplexity, or whatever score fits the task, gives you a direct picture of model quality. Measuring these on training and validation data helps you compare experiments without touching the test set too early. Those scores make it easy to compare models on the behavior you actually care about. Storing examples alongside predictions and labels helps when a metric looks odd, but the reason is not obvious. A few concrete cases often reveal data issues or systematic mistakes that a single aggregate number hides. A handful of examples can tell you more than a single summary score when something feels off. Speed tells you how efficiently the model processes data. That matters when two runs have similar quality but very different training times, especially for text models where tokens per second is the more meaningful measure. If one model trains much slower, that difference can matter just as much as the final score. System metrics show whether your hardware is the bottleneck. High memory use, idle GPUs, or saturated CPUs point directly to wasted resources or a training setup that needs tuning. Those measurements help you find inefficiencies that model metrics alone will miss. Some values matter because they change during training, such as learning rate, gradient norms, and weight norms. Watching them over time helps explain instability, clipping behavior, or the effect of schedules and regularization. It can help to record almost everything because the useful clue is not always obvious at the start. The trade-off is that too much tracking becomes noisy and distracting. So the real skill is choosing signals that improve observability without burying the important ones. Once runs are recorded well, comparison becomes much easier. A change in performance gives you a clue about what the modified component is doing, even if you do not fully understand it yet. A basic approach is to save the code and timestamp the results so the run can be reconstructed later. Dedicated tools go further by giving you dashboards and making it easier to share runs with the team. Versioning is about preserving the exact experiment ingredients, so the same result can be rebuilt later. That matters most when code and data both influence the model, because either one can change the outcome. common failure mode is discovering a good result and then being unable to reproduce it because the code changed, the parameters were lost, or the run was never saved carefully. The more moving parts there are, the easier it is for a small, unrecorded change to break reproducibility. ML systems depend on both software and datasets, so versioning has to cover both. Code versioning is standard now, but data versioning is harder and often neglected, even though it is just as important. Large datasets do not behave like source code. Copying them repeatedly, diffing them line by line, or keeping many local replicas quickly becomes impractical. A code diff works because lines are short and meaningful, but a data file may contain huge binary records where line-by-line comparison is not useful. For data, you often need a coarser way to detect what changed. Old versions of code can be stored as full copies, but that strategy breaks down when the dataset is massive. Storage cost and duplication quickly become the limiting factor. Code can be cloned to many laptops, but datasets often cannot. That makes the usual teamwork model for software much harder to apply to data. There is also a conceptual problem. For data, it is not always clear what should count as a meaningful change. A versioning system has to decide whether it cares about file contents, file additions and removals, or a checksum of the whole repository. Practical tools often settle for a simpler rule rather than trying to inspect every byte of the dataset. That gives a workable notion of change, even if it is not as detailed as code version control. Merge conflicts are another awkward fit. If two people train models on different dataset versions, combining those versions into one new dataset may not correspond to any valid model setup at all. When user data is involved, legal requirements can force deletion of records on request. That can make full historical versioning incompatible with privacy regulations. Good tracking improves reproducibility, but it cannot guarantee identical results by itself. Hardware, frameworks, and other sources of non-determinism can still change the outcome unless the environment is controlled carefully. A lot of experimentation is necessary because model behavior is still hard to predict from first principles. As understanding improves, fewer runs should be needed to find a strong configuration. Debugging ML is a separate challenge because failures can hide behind apparently normal training behavior. The main question is not just whether something is broken, but where in the system the problem actually lives. Any software project can have bugs, but ML adds extra friction. Problems can be silent, slow to validate, and spread across many different teams and components. The code may run, the loss may look fine, and the pipeline may complete without errors, while the predictions are still wrong. That is what makes ML failures dangerous. Neither the developer nor the user may notice right away. Fixing an ML bug is often not immediate, because a code change usually needs a full retrain before the result becomes visible. That delay makes debugging much slower than in ordinary software. An ML system can span data, labels, features, infrastructure, and a model itself. When something breaks, any one of those parts, or several together, might be responsible, which makes the search much harder. A useful way to debug is to classify the likely source of the failure. Then you can test whether the issue comes from the model theory, the implementation, the hyperparameters, the data, or the features. Sometimes the model choice itself is wrong for the structure of the data. If the assumptions do not match the task, the model can fail even when the code is correct. A linear model, for example, will struggle when the true decision boundary is not close to linear. In that case, the limitation is not a bug in the code. It is a mismatch between the model and the problem. Even a good model idea can fail if the implementation is wrong. Small mistakes in training or evaluation code can hide behind apparently reasonable outputs. A forgotten evaluation setting, a gradient that keeps updating when it should not, or another subtle coding mistake can spoil the result. The more moving parts the model has, the more carefully each one has to be checked. Hyperparameters can make the difference between a strong model and one that never converges. The architecture may be fine, but the training settings can still ruin the run. One setting can produce state-of-the-art performance, while another leaves the model unusable. That is why hyperparameter search is part of model development, not an afterthought. Data issues are one of the most common reasons a model behaves badly. If the examples are noisy, mispaired, or normalized incorrectly, the model may never learn the right pattern. Errors in collection or pre-processing can break the input signal before the model even sees it. Wrong labels, outdated statistics, or misaligned samples often produce poor training and poor evaluation results. Feature selection can help or hurt just as much as model choice. The model may fail if it is given too little information, or if it is given so much that it overfits or leaks the answer. Useful features carry predictive information, but extra or irrelevant ones can create noise and leakage. The balance matters because the model can only learn from what the features expose. A solid debugging practice has two sides: reduce the chance of bugs appearing and keep a procedure for locating them when they do. Both habits matter when building and deploying ML systems. There is no perfect debugging formula for ML, but experienced practitioners have found techniques that work well in practice. The next few methods are useful because they isolate complexity and make failures easier to reason about. The best way to debug a complex model is often to begin with the smallest working version. Once that baseline behaves sensibly, each added component can be tested against it. A shallow RNN before stacked 1, or one lost term before 2, makes it much easier to see which addition changes behavior. That stepwise approach turns a hard debugging problem into a sequence of smaller checks. If the starting point already contains many moving parts, any failure could come from almost anywhere. A simpler build first gives you a reference point, and that reference is what makes later debugging possible. Another strong check is to see whether the model can memorize a tiny data set. If it cannot do that, something fundamental is usually wrong in the implementation or training setup. Overfitting a handful of examples is a sanity test. If the model cannot drive loss very low on that small set, the problem is probably not generalization. It is the basic mechanics of learning. Randomness makes experiments hard to compare because each run can start from a different initialization or a different data order. Fixing the seed gives you repeatable runs, which makes both debugging and comparison much cleaner. When a seed is fixed, changes in performance are easier to attribute to the model itself instead of chance. That also helps other people reproduce the same behavior when they inspect your results. Distributed training tackles one of the hardest parts of modern machine learning, making large models train on hardware that is no longer enough by itself. The main questions are how to split the work, how to keep the workers coordinated, and how to avoid wasting compute. As models grow, the bottleneck shifts from clever algorithms to sheer compute and coordination. Scalability is difficult to learn well because it usually depends on access to large systems. So the practical goal here is to understand the resource problems and the choices they force. A lot of real-world training starts with data that is simply too large for one machine to hold at once. Medical scans, genome data, and large text corpora all create that problem. So the training pipeline has to work with data that arrives in pieces instead of all at once. Once the data exceeds memory, even the basic preparation steps need a different design. Zero centering, normalization, shuffling, and batching have to be streamed and parallelized, and small per machine batches can make gradient descent noisier and less stable. When a single sample is too large, checkpointing lets the system keep only part of the intermediate state and recompute the rest later. That extra computation can be worth it because it frees memory, and the freed memory can be used for larger batches or larger models. Data parallelism is the most common way to spread training across machines. The idea is simple. Give each worker the full model, split the data across workers, and combine their gradients so the model still learns as one system. Each machine processes a different shard of the dataset, but every machine keeps a full copy of the network. The hard part is not the local forward and backward pass. It is making sure the gradient information from all workers is combined in a way that still gives correct training behavior. If every worker must finish before the update happens, one slow machine holds everyone back. That straggler effect gets worse as the cluster grows, because a bigger group makes it more likely that at least one worker is delayed in a given step. If workers update weights independently, a gradient may arrive after the model has already moved on. That staleness means the update was computed for an older version of the weights, which can make optimization less reliable. The contrast matters because one strategy waits for everyone and the other keeps moving without waiting. That trade-off is the core design choice in parallel training: speed from looseness or stability from tighter coordination. The left side is the synchronized case. Each worker finishes, then the update happens together. The right side is the asynchronous case. Workers push updates whenever they are ready, which reduces waiting but opens the door to stale information. That figure makes the timing difference concrete. One version blocks on the slowest worker, and the other version keeps the system busy by letting updates arrive independently. When updates touch only a small fraction of the parameters, two workers are less likely to step on the same weights. In that sparse setting, asynchronous training can behave much more like synchronous training because the stale updates interfere less. If every machine contributes its own batch, the global batch can grow extremely fast. That often reduces the number of optimizer steps per epoch, so people try to raise the learning rate as well, but only up to the point where optimization stays stable. The same model can still be uneven in how much work different machines do. When one worker carries more load than the others, the cluster wastes capacity, so balancing the batch sizes is a simple fix even if it is not always the best one. Model parallelism takes a different approach. Instead of copying the whole model onto every machine, it splits the model itself across machines. That becomes useful when the model is too large for any one worker to handle efficiently. One machine might hold the first layers and another machine the later layers, or the work might be divided between forward and backward computation. The important idea is that different parts of the network live on different workers instead of every worker holding the full network. The split in the diagram is between full model replication and model partitioning. Track which machines hold copies of the whole network and which machines hold only a slice of it, because that distinction drives the communication pattern. The figure contrasts two layouts, one where every worker has the same model, and one where each worker owns only part of it. That difference determines whether the system is moving data shards or moving activations between machines. A split model can still behave like a chain if one part depends on the output of the previous part. A matrix split may run concurrently, but consecutive neural network layers often have to wait on each other, so the machines are separated logically even when the work is still serial in time. Pipeline parallelism breaks each worker's job into stages so different micro-batches can sit at different points in the network at the same time. That overlap keeps the hardware busier because one machine can start the next piece while another machine finishes an earlier piece. With four machines, one batch is split into smaller micro-batches and moved through the layers like items on an assembly line. While one micro-batch advances, another can already be in the next stage, so the forward and backward passes are both spread across the pipeline. Follow the handoff between stages. Machine 1 starts a micro-batch. Machine 2 picks it up after the first layer, and the later machines do the same in sequence. The important detail is that each machine is busy on a different micro-batch instead of waiting for the whole batch to finish. The diagram shows the forward and backward passes moving through the same pipeline. That repeating F and B pattern is what keeps the whole network trained while still overlapping the work across machines. Real systems often mix both strategies to get better hardware use, especially when one method alone is not enough. The cost is complexity because coordinating both data movement and model partitioning takes careful engineering. AutoML asks how much of model design can be handed to the machine itself. That matters because the search for a good model can consume huge amounts of expert time before any useful result appears. The idea is to trade manual trial and error for computation. Instead of a team trying many models by hand and settling for one that is merely good enough, the system can explore a much larger space and evaluate candidates systematically. Focus on the stage announcement and the reaction it triggered. That moment signaled a shift. Model building was starting to move from artisan work toward automation at scale. The figure anchors that announcement in a real industry event, not a thought experiment. It helps explain why AutoML became such a serious topic in production ML. A practical first step is tuning the knobs that control training. This kind of automation keeps the model structure fixed while searching for settings that make training work better. Hyperparameters are choices made before training starts, and they steer how the model learns. Small changes in these settings can change the final result a lot, which is why tuning them matters so much in practice. A model is not just its architecture, its training settings can make it look weak or strong. That is why good tuning can let a simpler model beat a fancier one on the same data. Manual tuning is common, but it is also unreliable and hard to reproduce. The joke works because it points to a real habit. People often keep adjusting settings by feel until the result looks acceptable. Once tuning becomes part of the workflow, teams usually reach for systematic search methods. Random search is simple, grid search is exhaustive but costly, and Bayesian optimization tries to use previous results to choose better candidates next. Not every knob deserves the same attention. Some hyperparameters barely change the outcome, while others have a large effect, so the important ones should get more of the search budget. The evaluation split matters here, because tuning can quietly leak information if the wrong data split is used. The warning is simple. Keep the test set untouched until the end. Validation data is for model selection, and test data is for the final report. If the test split influences tuning, the reported score stops being a fair estimate of real-world performance. The harder version of AutoML moves beyond tuning knobs and starts changing the model itself. That opens the door to searching for architectures and even learning the optimization rule that trains them. Now, the building blocks become part of the search. Instead of handpicking every layer and connection, the algorithm explores combinations and tries to discover a better design automatically. A neural architecture search system always needs the same three ingredients. The search space defines what can be built, the estimator scores candidates, and the search strategy decides where to look next. The search space is the menu of possible designs. It has to be constrained enough to search efficiently, but broad enough to include useful architectures. That means choosing the blocks and the rules for connecting them. Without those limits, the search becomes too large to handle. A candidate architecture has to be judged somehow, but full training can be too expensive. The estimator gives a cheaper proxy for how good that architecture might be. This is where the savings come from. If you have hundreds or thousands of candidates, full training for everyone can turn search into a massive compute problem. The last piece decides how to explore the space. Different strategies balance randomness, guidance, and compute cost in different ways. Random search is the baseline, but it can be too expensive for architecture search. Reinforcement learning and evolution try to use feedback from previous candidates, so the search improves over time. In practice, NAS often works over discrete choices, such as convolution sizes, activations, pooling, identity, or zero operations. The exact set depends on the base model family, like a convolutional network or a transformer. The training rule itself can be part of the search, but that is much harder. Optimizers interact strongly with their hyperparameters, so a choice that works on one architecture may fail on another. That idea leads to learned optimizers. Instead of hand-coding how weights should change, a neural network predicts the update from experience. A learned optimizer is not free. It needs data and training just like any other network. Training it separately for every task is costly, so the question becomes how to make it reusable. A better approach is to train the optimizer across many tasks, so it generalizes. Once it works well enough, it can even be used to train the next optimizer, which creates a recursive improvement loop. These methods are expensive upfront, so only a few organizations can pursue them at scale. Still, the payoff can be lower production cost, better efficiency, and sometimes model families that solve tasks older designs could not handle. Before choosing a model, it helps to know how mature the problem is. The right strategy depends on whether you are starting from heuristics, simple models, or already pushing against the limits of complexity. Each phase builds on the one before it. That keeps you honest, because a more advanced method should beat a simpler baseline before you invest in it. The first question is whether machine learning is needed at all. Often a simple rule or heuristic is the fastest way to get a useful result. A strong heuristic can already capture a meaningful fraction of the target behavior. That gives you a baseline and tells you whether the problem is even worth solving with ML. Early products often begin with a rule-based version before ranking models exist. Chronological feeds are a good example. Simple, functional, and easy to ship before personalization becomes necessary. Track the feed order and the absence of ranking logic. The important point is not the interface itself, but how little algorithmic machinery was needed at the start. The figure gives a concrete example of a non-ML baseline in a real product. It sets up the idea that a good default can be enough until the problem grows. That quote captures a practical truth. If a handcrafted rule already solves a large chunk of the problem, ML may only add the remaining improvement. Sometimes that remaining gain is worth it, and sometimes it is not. When a heuristic stops being enough, the next step is usually a simple model. The goal is clarity and a dependable pipeline, not complexity for its own sake. Simple models help you see whether the data and labels make sense. They are also easier to debug, deploy, and improve, which makes them ideal for establishing a working ML system. Once the pipeline exists, the focus shifts from getting any model working to getting the simple model working well. This is often where the biggest practical gains come from. At this stage, improvement comes from careful search and better inputs. Changing the objective, engineering features, collecting more data, and combining models can all move performance without changing the overall system shape. Only after the simpler options have been pushed far enough does it make sense to reach for complex models. By then, you know the problem is worth the extra cost, and the system can support it. More complex models can help when the task really needs them, but they are not the first move. The point is to earn that complexity with evidence, not assumption. Production work does not end at training accuracy. A deployed model will drift, so the surrounding infrastructure has to support retraining at the pace the real system demands. Offline evaluation answers a practical question. How do we judge whether a model is good before it affects real users? That matters because a model can look promising during training and still fail on the task the business actually cares about. That question becomes hard when the real cost of failure is hidden. If a drone system misses intrusions and you never measure those misses, then accuracy numbers alone may give a false sense of confidence, and choosing between algorithms becomes guesswork. A model only becomes useful when its score reflects the decision people actually need to make. Working with the business team helps turn vague success into concrete metrics, so the model is judged by the right standard instead of a convenient one. That difference creates a real gap between training and deployment. During development, labels let us measure error directly, but once the model is running, those labels may arrive late or never arrive at all. Some tasks give us a partial signal from user behavior. A click on a recommendation can stand in for a useful label, but that signal is biased because clicks depend on position, visibility, and many other factors beyond true quality. Other systems need a different strategy entirely. If performance cannot be measured directly in production, then monitoring becomes the safety net that watches for drift, failures, and changes in behavior over time. The pre-deployment step is where good comparison starts. First, we need baselines to compare against. Then we need evaluation methods that go past a single accuracy score and reveal how the model really behaves. Baselines give a metric meaning. Without them, a score like FID or F1 can sound impressive even when the model is no better than a trivial rule. A single number by itself does not tell you whether a model is actually useful. You need a reference point so you can judge whether that number is better than chance, a simple rule, or something a human would accept. Class imbalance can make a score look good even when the model is doing almost nothing. If one class dominates the data, a model that mostly predicts that class can achieve a deceptively strong F1. So the baseline tells you whether the result has real value. That comparison is the whole point of evaluation. Different tasks call for different baselines, but the idea stays the same. Measure your model against something simple, familiar, or already available before drawing conclusions. The first reference point is pure chance. If a model cannot beat random predictions, there is no evidence that it has learned anything useful. The exact answer depends on how the random outputs are generated. Sometimes each label is equally likely, and sometimes the random guesses follow the same label frequencies as the dataset. With imbalanced labels, the random baseline can look very different depending on the sampling rule. Working out those numbers by hand is useful because it trains your intuition for how much a metric can be distorted by the class mix. These values show why raw metrics can be misleading. Accuracy rises when a random guess matches the majority class often enough, while F1 can still stay very low because the minority class is poorly captured. The next reference point is a hand-built rule. Before reaching for machine learning, it is worth asking what a simple heuristic can already do on its own. A useful heuristic can be surprisingly strong when the problem has a natural ordering or an obvious shortcut. In a ranking task, for example, a rule like reverse chronology gives you a practical starting point for judging whether a learned ranker is actually adding value. A zero-rule baseline is the simplest heuristic of all. It ignores almost everything and always predicts the most common class. This baseline matters because it sets a very low bar that many models still fail to clear by much. If a learned system cannot outperform the majority class guess, then the extra complexity is not paying for itself. For recommendation problems, the most frequent item is often a strong baseline. A model should improve enough over that rule to justify its cost, especially when the simpler method is already accurate a large share of the time. When a task involves judgment or skill, human performance becomes the most important reference point. The question is not only whether the model scores well, but whether it matches the standard people already trust. That comparison matters both for automation and for assistance. A self-driving system, for example, has to be judged against human drivers because users care about safety and trust, not just a numerical gain on a benchmark. Another useful reference is whatever already solved the problem. Sometimes the competition is not a person or a random guess, but business logic or a third-party tool that users already rely on. A new model does not always need to be better in every raw score to be worthwhile. If it is cheaper, simpler, or easier to deploy, a slightly worse model can still be the better choice in practice. That distinction matters throughout model evaluation. A system can improve on the old one and still fail in the real world if people do not trust it, and another system can be imperfect yet still useful if it helps users do their job faster or better. Evaluation methods go beyond a single score and ask whether a model is robust, fair, well calibrated, and useful in real settings. A model can look strong on a benchmark and still fail once real users, messy inputs, or unfair patterns show up. The methods here help measure those hidden properties so deployment decisions are based on more than accuracy alone. Perturbation tests ask how stable a model is when the input is slightly disturbed, because real data is rarely as clean as training data. A model that learns from tidy hospital recordings may not survive the messiness of real user recordings. When the training environment is too different from the deployment environment, a model can fail even if it looked excellent during development. Background chatter, music, different microphones, and even a slight delay in starting the recording can all shift the input enough to confuse the model. Those small differences matter because they are exactly the kinds of changes users produce without trying. Ideally, the data used for training should resemble the data the model will face later, but that often is impossible. When the real world is noisier than development, the best model on clean data is not necessarily the best model on messy data. A practical check is to inject small, realistic changes into the test data and see which model holds up best. If one model stays accurate under noise while another collapses, the first one is the safer choice for deployment. A fragile model can drift with tiny changes in user behavior, device type, or recording conditions, which makes it harder to keep working well over time. The same fragility also creates room for adversarial attacks, where someone deliberately tries to break the model. Invariance tests check that changes to sensitive or irrelevant inputs do not change the output, because some features should never affect the decision. If race information disappears and the mortgage decision changes, that is a sign the model is using something it should not use. The same concern applies to names in resume screening or gender in pay decisions. The core idea is that the output should stay stable when only protected attributes change. When it does not, the model may be biased enough to be unusable even if its average accuracy looks fine. One way to check for this problem is to keep the rest of the input fixed and swap the sensitive attribute to see whether the prediction changes. A better safeguard is to leave those features out of training altogether when they are not meant to influence the decision. Directional expectation tests check whether the model changes in the direction common sense predicts when an input moves up or down. For house prices, larger lot size should not lower the predicted price, and smaller square footage should not raise it. When the model moves the wrong way, it is learning the wrong relationship and needs closer inspection before deployment. Calibration asks whether predicted probabilities mean what they claim to mean, which is crucial whenever a model reports uncertainty. A probability estimate is useful only if it matches reality over many predictions. If a model says it's 70%, but the event happens 60% of the time, the model is overconfident. A calibrated model would bring that estimate down to 60%. Practitioners often focus on ranking or accuracy, but reliable probability estimates are what make a forecast trustworthy. A model that is well calibrated gives you better decisions whenever the exact probability matters. In a recommender system, calibration can mean the mix of recommended items should reflect how users actually behave, not just which item looks most likely in isolation. If a user watches romance 80% of the time and comedy 20% of the time, a calibrated system should reflect that balance. For ad ranking, the best ordering may be enough if the goal is just to choose the top ad. But if you need to estimate total clicks, the probabilities themselves must be accurate, or your forecast will be off even when the ranking is correct. A simple way to measure calibration is to group predictions by confidence level and compare predicted probability with observed frequency. If the curve follows the diagonal, the model's probabilities are behaving well. Scikit-learn provides a direct way to draw that curve for binary classifiers. The diagonal line is the target because it represents perfect agreement between predicted confidence and observed outcomes. The logistic regression curve sits closest to that line here, which fits the fact that it directly optimizes a loss tied to probabilistic predictions. Different models can rank examples similarly while still producing very different probability estimates. This figure makes the gap visible by comparing each model's curve against the ideal calibrated line. When probabilities are misaligned with reality, a post-processing step like Platt scaling can often bring them closer to the truth. The main idea is to transform the raw scores into probabilities that better match observed outcomes. Confidence measurement focuses on whether a model is certain enough to trust on a per-example basis, not just how well it performs on average. A system that reports every prediction without checking confidence can annoy users at best and cause serious harm at worst. The practical question is whether the model should speak up, defer to a human, or ask for more information when it is unsure. The hard part is choosing the cutoff for action. Below that threshold, the system needs a policy. Drop the prediction, route it for review, or gather more evidence before deciding. Average metrics tell you how the system behaves in general, but confidence is about individual examples. That matters whenever every single prediction has to be safe or reliable. Slice-based evaluation breaks the data into meaningful subsets so you can see where the model is strong, where it is weak, and where it may be unfair. Overall accuracy can hide very different behavior across groups. If you only watch one course metric, you can miss both unfairness and opportunities to improve the model. When a majority group dominates the data, the overall score often reflects that group much more than the minority group. That means a model can look strong while still failing the people who are least represented. One model may have a high average score because it does very well on the common cases and poorly on the rare ones. Model A looks excellent at first glance, but the minority slice tells a different story. That gap is exactly why a single overall number can be misleading. A second model can trade a little overall accuracy for much more balanced behavior across groups. Model B gives up a small amount of overall accuracy, but it treats both slices much more evenly. Depending on the application, that balance may be the better decision. That choice depends on whether you care more about a slightly higher aggregate score or more consistent performance across groups. A slice view gives you the information needed to make that trade-off deliberately instead of accidentally. The table makes the trade-off explicit. One model wins on overall accuracy, while the other is more even across subgroups. Seeing the numbers side by side prevents the majority slice from hiding a serious weakness. If a company only looks at the aggregate score, it may deploy a model that quietly disadvantages an underrepresented group. Slice-based metrics reveal that problem early and can also point to concrete improvements in the weak subgroup. Not every subgroup matters equally. For churn prediction, for example, paid users may deserve more attention than free users because mistakes there have a bigger business impact. Simpson's paradox is a reminder that combining groups can hide the true pattern inside them. A model can look worse overall, even while it performs better in each subgroup, so the aggregate alone can point you in the wrong direction. The table gives a classic example. One model loses on the total, even though it wins inside both groups. That kind of reversal is exactly why the slice view matters before making a decision. The Berkeley admissions data are often used to show how misleading totals can be. The overall number suggested bias against women, but department-level rates told a more complicated story. Looking inside each department changes the interpretation completely. That is the general lesson. Totals are useful, but they are not enough when groups are mixed together in uneven ways. Slice-based evaluation helps with fairness, with debugging, and with finding non-ML problems that only appear in one subset of traffic. A weak mobile slice, for example, may turn out to be caused by a hidden button rather than by the model itself. A detailed view of performance also helps you explain the model to other stakeholders. When people can see how the model behaves on the slices that matter to them, they are much more likely to trust the deployment decision. The remaining question is how to discover which slices deserve attention. That process is partly systematic and partly exploratory, so the next step is to use a few practical approaches together. A simple starting point is to use domain knowledge and define slices that already make sense for the task. These are the groups you would naturally worry about before touching the data. For web traffic, that might mean slicing by mobile versus desktop, browser type, or location. These groups often behave differently, so checking them separately can uncover problems the average metric hides. Another route is to inspect the mistakes directly and look for repeated patterns. Misclassifications often cluster around the same kind of user, device, or input condition. If most of the wrong predictions come from mobile users, that pattern points straight to a useful slice. Error review is often the fastest way to discover where the model is failing. When manual inspection is not enough, automated methods can search for slices that stand out. The goal is to generate candidate groups, filter out the unhelpful ones, and rank the rest by how informative they are. Researchers have built systems that use beam search, clustering, and decision methods to propose promising subgroups. Those candidates are then pruned and ranked, so the most informative slices rise to the top. Once a slice matters, it still has to be measured well. If the data for that slice is sparse or mislabeled, the evaluation can mislead you. So the quality of the slice data is just as important as finding the slice itself. This chapter pulls together the core ideas behind choosing, building, and evaluating machine learning models. The main point is that good model work is not just about accuracy. It also depends on constraints, experimentation, scale, and trustworthy evaluation. The model is the part that turns all the earlier data and feature work into something you can test against the real task. Once the model can predict outputs from inputs, the whole pipeline starts to answer whether the original idea actually holds up. Model choice is less about ranking every architecture and more about matching the job in front of you. A useful model fits the problem, the available resources, and the quality bar you need to meet. Development often starts with one strong model, but combinations of models can improve results when you need more robustness or better competition performance. Ensembles are common because different models make different mistakes, and combining them can smooth out those errors. Experimentation creates a lot of versions very quickly, so manual tracking breaks down fast. Good tooling matters here because it keeps the results, code, and model versions tied together without turning the process into bookkeeping. As models and datasets grow, training on one machine becomes too slow or too limited. Parallel strategies, such as data parallelism, model parallelism, and pipeline parallelism, let the work spread across multiple devices, but they also introduce serious systems complexity. A metric only has meaning when you compare it against something sensible. Baselines and quick sanity checks help separate a model that truly improves the task from one that merely looks good on paper. Offline evaluation can only go so far because production adds real traffic, real data shifts, and real constraints. The model's behavior becomes clear only after it is deployed and exercised in the actual environment. More data is not a universal fix. If the model is underfitting, extra examples usually do little, but if the model is overfitting, more training data can reduce that instability and improve generalization. Some winning competition solutions rely on a surprisingly large number of models. That pattern shows how much performance can improve when many weak points are covered by different predictors working together. Class imbalance is one place where bagging, boosting, and hybrid methods show up often. These methods can give the minority class more effective influence and make the classifier behave less narrowly around the majority examples. Stability during training matters because erratic loss usually points to optimization trouble or noisy updates. A smoother loss curve makes it easier to trust what the model is learning. Bagging works by training multiple predictors on different samples and then combining their outputs. The averaging reduces variance, which is why it often helps models become less sensitive to the quirks of a single dataset. Solution write-ups for machine learning challenges are worth studying because they show what worked under pressure. They often reveal practical tricks that are not obvious from theory alone. Boosted trees have a strong record in structured data problems and competitive settings. They combine many simple learners in a way that steadily corrects earlier mistakes, which is why they remain such a common choice. Some of the practical monitoring questions belong to the deployment and production side of the system. That topic sits later, after the model has been built and evaluated. Many teams know tracking matters, but they still avoid it because the manual work is tedious. The useful fix is to make the process automatic enough that version history is captured without extra effort. Distributed and GPU computation can introduce small run-to-run differences even when the code is unchanged. In practice, that means perfect reproducibility is sometimes limited by the underlying math and the order of operations. A model that works well in testing still has to survive real user traffic. Very large serving systems raise their own engineering problems, and those are outside the narrower model building focus here. When data does not fit in RAM, the algorithm has to process it in pieces instead of loading everything at once. That constraint changes how training and pre-processing systems are designed. Checkpointing keeps only part of the intermediate state and recomputes the rest when needed. That saves memory during training, which becomes important when models are too large to fit comfortably on one device. Synchronous SGD waits for workers to finish before updating shared parameters, so the team stays in step. That coordination is simple to reason about, although it can become slower when one worker lags behind. Once training is split across machines, the slowest worker can hold everyone back. That is why distributed systems often need strategies for heterogeneity and straggle mitigation. The move to large deep networks depended on systems that could coordinate many devices efficiently. That shift is what made very large models practical at all. Framework support matters because distributed training is hard to implement from scratch. Tools that package the coordination logic let engineers focus more on model design and less on low-level communication details. Lock-free updates can speed up optimization by reducing synchronization overhead. The trade-off is that updates may collide, so the method works best when some noise is acceptable. Recent language models show how far training systems have stretched in size and compute demand. Their success depends on the same distributed ideas, just pushed to a much larger extreme. Batch size affects more than speed. It also changes how the optimizer moves through the loss landscape. That is why data parallelism and batch scaling have to be studied carefully, not treated as mechanical details. For the system side of machine learning, it helps to learn from lectures and course material as well as papers. The concepts tend to connect across sources, especially when the goal is understanding scale and parallelism. Pipeline parallelism assigns different layers or stages to different devices, so each part of the network works on a different slice of the batch. It is one more way to fit and run very large models efficiently. Model compression techniques belong to the deployment side of the story, where size and latency start to matter more. That topic is handled after the model building chapter. The joke reflects a real pattern. Many model designs are still shaped by trial, error, and intuition. Even when the process is informal, there is often a serious search strategy underneath it. Automated tools can help narrow the model choice before manual tuning starts. That saves time when the space of possible models is already large. Random search is often a strong practical baseline for tuning because it explores the space broadly and cheaply. A framework-agnostic tool is useful when you want that process to work across different model libraries. A course-to-find strategy avoids wasting effort on tiny adjustments before the important region of the search space is known. Once the space is smaller and more promising, more targeted methods become worth the cost. Architecture search tries to automate part of the model design process instead of handcrafting every choice. The goal is to let the system explore promising structures when the design space is too large to search manually. A continuous relaxation makes search easier to optimize with gradients. After that, the result has to be converted back into a discrete architecture that can actually be built and deployed. The way a model learns can matter just as much as the model structure itself. Optimizers, update rules, and training procedures often decide whether training is stable and effective. Some research pushes optimization one step further by learning the optimizer as well as the model. That idea is interesting because it blurs the line between training a network and designing the training rule. Scaling the network in a controlled way can improve both accuracy and efficiency. Efficient design matters because better performance should not come at an unreasonable compute cost. Real-world systems rarely stay fixed for long. The model you ship is usually part of a moving product environment, so architecture choices eventually need revisiting. Ranking systems often go through dramatic changes as data, product goals, and user behavior evolve. That history is a good reminder that the surrounding system shapes the model as much as the model shapes the system. Good ML engineering depends on habits that keep the system testable, stable, and aligned with the product goal. Those rules become useful because they turn experience into repeatable practice. How often a model should be refreshed depends on how fast the world changes around it. That question belongs to the continual learning and update strategy discussion later on. A model only matters when it supports the product objective that the business actually cares about. If those goals drift apart, metric gains can become misleading. Some metrics are designed for generated content rather than standard classification. For image synthesis, lower values usually indicate that the generated images look closer to the real data distribution. A number like 0.80 is only meaningful when the task and baseline are clear. Without context, the same score can be either weak or strong. F1 does not treat mistakes in both classes the same way, so the interpretation depends on which kind of error matters more. That is why metric choice has to match the problem structure. Noise can come from many small changes that make examples less clean without changing their meaning. Those variations make training harder because the model has to learn the real signal underneath them. Data is not neutral when it encodes unequal outcomes from the world. That is why bias and fairness concerns have to be considered before a model is trained and deployed. Some features are not just ethically questionable. They may also be legally restricted. That creates a hard constraint on what can safely enter the training set. Calibration matters when recommendation scores are used as if they mean something precise. A calibrated model gives scores that line up more closely with actual likelihoods, which makes them more trustworthy. Face recognition failures can have real and damaging consequences when systems misclassify people unevenly. That example shows why error analysis has to include fairness, not just raw accuracy. Old datasets often preserve the patterns of the institutions that created them. When those patterns include discrimination, the model can learn and reproduce it unless the data is examined carefully. User experience is not universal, so models that interact with people need to respect cultural context. That perspective matters when the product depends on how different users interpret or trust the system.